All right, taking a look at solving two-step equations today, which we'll find out is really just a series of one-step equations. In this case, two one-step equations. So the essential question here is how do you solve an equation that contains multiple operations? And you're going to find out what we're trying to tell you is take it in multiple parts. So we'll reverse or take the inverse of one operation at a time. Remember, if you're watching this, click present to get the full presentation. That's how you can watch the video and everything. That's the warm-up we did in class. So this essential understanding here pretty much says exactly what I just did, just with fancier words. Okay, when you're solving two-step equations, you use the properties of equality. That's where we can add the same thing to both sides and it doesn't change, etc. Inverse operations, which is if you have addition, you're going to use subtraction to undo it. Multiplication, you're going to use division, and so on. Look at 2.1 if you want to review properties of equality or inverse operations. And then to form a series of simpler equations. All right. Equivalent just means, once again, that because we used these two things, they stayed equal. It stayed true. So we can use them repeatedly to isolate the variable. Now, our next lesson will be multi-step equations, which is really the same thing, just there's more than two steps. So here's our first example we're looking at. It says, what is the solution for 2x plus 3 equals 15? Now, this is an example. So if you click it, it's going to unmask it as you go. All right, so this was a plus 3. Now, if we're reading the book, it gives some great techniques. Most of us will, in the end of this chapter, will be able to look at this and be like, oh, I want to subtract 3 first to undo the plus 3, and then I'll divide by 2. Because there's two operations here, all right? What we really have here is if we look at what's happening to the x, what we really have is we're multiplying by 2, and then we're adding 3. That's what this function is doing to the x. If I plugged in like x equals 5 and solved it, I'd multiply by 2 and then I'd add 3. That's what this function is doing to the x. To reverse it, which we call inverse, okay, we're actually going to do the exact opposite in the opposite direction. So if plus 3 was the last thing, minus 3 will be the first we do. If times 2 was the first thing, then dividing by 2 will be the last thing we do. So these are our two steps. We're going to subtract 3. You can already see that kind of came out to be real here. When I do that, I'll unclick it in a minute, but remember the 3 and the minus 3 were 0, so 2x plus 0 is just 2x. 15 minus 3 is 12. And like I said, our second step would be the opposite of multiplying by 2, which is dividing by 2. So once again, we'd come in here, we'd divide both sides by 2, and we'd get that x equals 6. So once again, you'll get comfortable just looking at this and say, I'm going to subtract 3 from both sides. Now, you could have divided by 2, but then you'd have fractions. If I had divided this by 2 first, yes, this would have become an x, but then I would have had 3 divided by 2, and I would have had 15 divided by 2. This works, and it will in fact get you the right answer. If you subtract 3 halves from both sides, you'll have 12 halves, which is 6. So this would work, but we're looking for the easiest, most efficient path, and that's why we chose to subtract 3 first. All right, so if you follow this kind of pattern, look at what it did to the x and reverse that, and that's usually going to be your best path to the quickest solution. All right. So then after the example, it gives you the U try. Now you can't click away these boxes because the U try is for you to try. And then we go over it in class, which is what we did today. So you can see here, if I'm solving this, same thing. If I look at what's going on with this problem, if I look, hey, what did they do to the variable? Well, they divided by 2, and then they subtracted 3. So if I'm going to do the opposite, I need to add 3. Remember, I'm doing the reverse direction as well. And then times by 2. So if I go back to here, you can see to undo a minus 3, I added 3 because those go away to 0. And then I had to add 3 to the other side to balance it all out. So that's what that was saying. Step 1, add 3 to both sides. So I end up with 8 equals t over 2. And then it says here my next step is to multiply both sides by 2. And we could have seen that here as well. Notice that if I multiply both sides by 2, that's division, so I'm going to multiply. So you don't have to scout out your path ahead of time. But if you're struggling with what to do, this is a great way. Like if I plugged a number in for t, what would I do? I'd divide it by 2 and then subtract 3. So I want to do the reverse. All right. So when the other key concept that we're looking at, because it's a little bit different, but it works the same, is if there's more than one term in the numerator. Like here, instead of just being x over 3, it's x minus 7 over 3. So we could use the method we just talked about. If I look at, okay, if I plugged an x in here, first thing I'd do is subtract 7 and then divide by 3. So I want to multiply by 3 and add 7. But you can also see it here. If I added 7, I have to add a fraction because this is really 7/3. It gets super ugly really fast. But if I follow this, times 3 and then add 7, there's the bell, then I'm going to come out with something that looks really nice. Okay, timesing by 3 here, you could see that, once again, this is something we'll call fraction busters later, but if I have a fraction and I want to get rid of it, the fastest way is to multiply by the denominator. This denominator, all right, the 3 is what we multiply by. Remember, we can think of this as 3 over 1 if we want, doesn't matter. But some of you will think, oh, that cross cancels. That's great. Just remember the reason it crosses cancels because 3 over 3 is equal to 1. The numerator and denominator are the same. All right, so that's the theory behind that. But it's also okay at this point if you're like magically, hey, look, it disappears. But in the back, I want you to know why it magically disappears. Notice we went from this super ugly equation to this one with a pretty easy step. And most of you, if I gave you this, you'd feel very comfortable saying, oh, I need to add 7 to both sides because this is a minus 7. So if I add 7, those go to 0. I have to add 7 to the other side to balance it all out. All right, we have one more example like this now that I've fixed the slides. And this was 6 equals x minus 2 over 4. So once again, if I'm kind of thinking ahead, I know that this, if I look at what's happening to x, if I plugged in a number here, I'd have to subtract 2 first and then divide that by 4. So if I'm doing the opposite, I'm going to multiply by 4 and add 2. Awesome, an announcement. There you go. Anyway, so if I start looking at it from that angle, 6 equals x minus 2 over 4. So like I said, first thing I'm going to do, I'm going to multiply both sides by 4. Now once again, I don't need this little trick over here. If I look at this, hey, I want to undo division of 4, I multiply by 4. All right, and remember those cancel to 1. So 4 times 6 is 24. Which is equal to x minus 2. And then, as we said before, but even without this, looking at the problem, I would have been like, okay, now I need to add 2 because I want this to go to 0 so that I have x all by itself. But that means I have to add 2 to the other side as well. So when I'm all done here, I end up with 26 is equal to x. And once again, I could go plug that in. 26 minus 2 is 24. Divided by 4 is 6. So it does seem to check out. All right, now we're going to keep doing this. We are never going to be done with solving equations in this class. So we will get a lot of practice. This is just the beginning. So don't get freaked out. Take it one step at a time, and it will kind of work into itself and be a lot easier that way. All right, I hope that helps.